Alright, so this is the instability strip where the variable stars are. And these are stars that are have left the main sequence because they've exhausted their hydrogen fuel supply. The main thing is as it says down here, is these stars basically will trap the radiation that's produced by the core, and they heat up and expand. So the solar atmosphere, the star's atmosphere, will expand, and then it cools down and contracts. And that's the whole idea of the variable stars, right? They're pulsating, and we see that all over the universe when we look out, not just in our galaxy but in other galaxies as well. We see these variable stars, and what's really important about them, well, that is this. Okay, so this is the next slide. Is there's a relationship between the period of a variable star and its luminosity. So and of course, we're talking about the absolute luminosity, right? Not the luminosity because of it's closer or further away. It has nothing to do with that. So basically, what this allows us to do is, by observing the period of a particular star, let's pick one of the Cepheid variables, for example. So if you find a Cepheid variable and it's close enough to use the parallax method, which there's plenty of Cepheid variables where that's a true situation. You can directly measure the distance to that Cepheid. Then you have a standard by which you can measure the distance to other Cepheids of exactly the same period, right? So if it's the same period, then it has the exact same luminosity, right? So imagine a Cepheid much further away, even in another galaxy, for example, but it happens to have the exact same period as the Cepheid that you've measured using the parallax method. All right. So if you see that, if you measure the period of that Cepheid, then you know what the luminosity has to be. All right. So what the absolute luminosity has to be, and so you measure that, and then you use the inverse square law in reverse, if you will, to figure out the distance to that particular Cepheid variable. That has the exact same period as the one that you measure. You measured the distance directly, within our galaxy, and of course this works for other Cepheids that are have other periods. So we just have to measure the distance to those different Cepheids with different periods. But if you know the period, which is something you can directly measure, right? You just sit there and watch the star over a period of time, and then wait for its brightness to dip, and then brighten again, and then dip again, and so that's one complete cycle, and so you'll know what the period is, right? Because that's what the period is the time to complete one full cycle. All right, so that's variable stars. All right, let's keep moving here. So the death of a solar type star, like a star like the sun, it'll spend, ours will be about 10 billion years, but some of them can be up to 11 to 12 billion years, and so they're just converting hydrogen into helium. That's also called helium hydrogen burning. And then eventually the star becomes, as it runs out of its hydrogen fuel supply, it becomes a red giant. It spends roughly 1 million years, give or take, converting helium, fusing helium in the core, into heavier elements. All right, so what eventually happens with these stars is they essentially lose the gravitational grip on the outer part of the atmosphere of the star, and that star shows what's known as the planetary nebula effect. There's the atmosphere leaves, the outer atmosphere of the star leaves the star and escapes out into space, and we see these planetary nebula all over in our galaxy and other galaxies as well. And let's see, so this is the red giant stage, then the planetary nebula, and then eventually, after all the planetary nebula has dispersed and gone out into space, what remains settles down into this dead star called a white dwarf. So that's for low mass stars, right? And there's some pictures of planetary nebula. This is one that's actually in false color. A lot of times in astronomy, we'll filter different colors so that we get a sense of of more detail in the picture. There's another planetary nebula that are not all perfectly circular. All right, so what about these massive stars, right? So that's the other. Remember, there's basically two categories of stars: massive stars and low mass stars. Our sun, of course, would be considered a low mass star. So when you get to massive stars, and generally what we do is, as far as massive stars, we think of massive stars, anything certainly 10 times the mass of the sun or greater is considered a massive star. All right, so anyhow, these stars will continue to fuse beyond hydrogen, beyond helium, and fuse other elements, as it's showing right, in this picture right here. And it'll fuse all the way up to iron. All right, and this process of creating all the elements that we find on the periodic table with massive stars is called nucleosynthesis. Okay, and that is remember the star can only fuse up to iron, right? Iron, of course, is element 26. But then you might ask, well, how do we get all the other elements and that exist in the universe? And that, of course, comes from massive stars, right? These massive stars will try to squeeze iron and fuse iron, but the fusion of iron doesn't release more energy, as it says right here. It won't release any more energy. So you see, if you fuse these lower, these less massive elements, then the next element that's created releases more energy when it does that. Right, the star releases more energy, but when it gets to iron, that it peaks, and then it doesn't release any more energy. But that's of course a problem for the star, because remember, gravity's always pulling inward, and the outward push is coming from the fusion of heavier and heavier elements for these massive stars. But when the star tries to fuse iron, it fails, and what happens is the core shrinks in a very, very rapid fashion, and protons and electrons that are part of the star will actually merge in a nuclear process and form neutrons, and the neutrons will crush the star down to something roughly the size of the Earth, and sometimes it'll even go smaller than that, and you have this extremely dense ball of neutrons, and they basically smash into each other at the core, and this all happens in a matter of seconds at the end of a star's life, and you have the result is what's called a supernova. Okay, and a supernova is, the explosion of a massive star, the death of a massive star. And that's actually when all the heavier elements, heavier than iron, are created. It's during the supernova explosion. Let's see. And of course, the thing about this is this material is ejected by the supernova explosion back out into space, right? This material is created, heavy elements, for example, gold and platinum and uranium, and that explosion pushes those atoms out, those newly created atoms out into space. Also, by the way, the supernova releases an incredible amount of what are called neutrinos. These are massless particles that travel at the speed of light. But the reason we bring that up is we can actually measure that. We can measure the amount of neutrinos that are coming. All right. So and one thing to note is these supernova explosions are so incredibly bright that for a small amount of time, like so if you look at the picture right here, the star can actually outshine the rest of its galaxy. Now, let's say a galaxy has 100 billion stars. That's a rough estimate of like a spiral galaxy like ours. So a single star, right, can outshine 100 billion other stars for just a short amount of time. And that's, of course, that's the supernova explosion. That's what is releasing this tremendous amount of energy with it. All these new, heavier elements are created. This picture right here is what's called a supernova remnant. There are other supernova remnants. There are actually two really famous supernova remnants. One is called the Crab Nebula. It's in the constellation Taurus. It was actually a supernova that exploded in the year 1054 AD. And there were Chinese astronomers who actually measured, who wrote down this, this new star, this supernova that was seen in the constellation Taurus, and it's still there, of course. You can't see it anymore without a telescope, but this is what it looks like. This is the supernova remnant, and of course it's expanding. We can measure the speed that it's expanding, and of course when you measure the speed at which the gas is expanding, all that gas comes back to get, if you basically reverse and ask yourself, well, if it's traveling at this speed, how long ago did it all come together? And of course that turns out to be the year 1054. And of course we have visual confirmation of that from these Chinese astronomers, more than 1,000 years ago. All right, so and then there's actually a recent supernova called supernova 1987A, and this actually occurred in the southern hemisphere and was observed. The thing that's important about this one is, well, first of all, it was a visual supernova. There are supernovas going off, all the time if you count the entire universe. But it's rare that a human can look up into the night sky and see this. This supernova occurred, as I said, in the southern hemisphere, and there were modern telescopes that were actually able to measure that, and that's that's the importance of this one. It gave us tremendous amounts of information. It's still giving us a great deal of information. All right, I'll pick up in the next video.